So, let us recall that an A module M is said to be Noetherian if it satisfies the ascending chain condition. Ascending chain condition, and M is said to be Artinian if it satisfies the descending chain condition. So, we saw some examples of Artinian modules, Noetherian modules which are not Noetherian but Artinian, and modules which are not Artinian but Noetherian. Another example, did we discuss this example? Look at this, fix a prime P and take H to be set of all A by P power n, A belongs to Z and n bigger than or equal to 0. This is then H is neither Noetherian nor Artinian. Right, because this has if you take so you can think of this see this is a Z module, you have H2 the group that we discussed last time, that G is all elements of order a power of prime power of P. Okay. So, you have a surjective map from H to G, okay, and you take any ascending chain that will lead to an ascending chain here which does not terminate. So, here an ascending chain cannot terminate, but any descending chain here, descending chain also cannot terminate. If I take what are the subgroups of H, there are no finite subgroups here, because if you take some A by P power n is there, then you know N A by M A by P power n is also there for all M and Z. So, you can easily see that okay, one can produce a descending chain. H is not Noetherian there exists onto Z module homomorphism. Z is not therefore, the Z is not Noetherian, and you can see this other way. H is not Artinian because Z is a submodule of H, right. Z is a submodule of H implies H is not Artinian. H has all Z here, right. See, if I have you take an ascending chain here, suppose we know that every ascending chain terminates. Okay. Now, look at that ascending chain in G. In G it cannot terminate. Okay. There exists a chain in G, and we should in fact say that way, like there exists a chain in G which does not terminate, right. G1 which is group of all, G1 is the identity element, G2 is all elements of order p square, then G3 is all elements of order p cube and so on. Now, look at its pullback in H, and then that will be a strictly ascending chain which will not terminate at all. So, therefore, this is not Noetherian. Similarly, Z is contained in H. So, I can think of this 2Z contained in 2 square Z contained in, this is a chain in H in G and hence in H. Which does not terminate. This is a strict chain of submodules in Z, right. Sorry, this is the other way. I want to say that sorry, this is in Z. Okay. Another example is Kx is Noetherian but not Artinian. G is the so G is subgroup of Q mod H, Q mod Z with all elements of order which is a power of P. Kx is Noetherian but not Artinian, and if you look at this, see, Noetherian property is not it does not pass on to the substructures always. For example, if you take k x square xy xy square, this ring, this is a subring of k xy. Well, okay, so let me not do this right now because we do not know whether k xy is Noetherian or not. So, let us look at this k x1 x2 infinitely many variables. Okay. This is not Noetherian. This is neither Noetherian nor Artinian, because you can have this chain x1 contained in x1 x2 contained in x1 x2 x3 and so on. That will be a strictly increasing chain which never terminates. So, therefore, this is not Noetherian, but you can have this if you look at the the field, the fraction field of this ring. Any field is Noetherian because there is only one ideal in a field, one proper ideal which is 0. So, therefore, if you look at all submodules of I mean the field, it's there is only one proper submodule, there is only one, or if you collect all submodules there are only two, which is the whole ring and 0 itself. So therefore this a field satisfies ascending chain condition, descending chain condition, etc. But so therefore this is Noetherian, but this is not. Subrings need not be Noetherian even if your the original ring is Noetherian. But now in the case of modules this is not precisely the case. Suppose I have a Noetherian M is a Noetherian A module, M is an A module, so look at the collection of all. See, if a module is not finitely generated, okay, suppose a module is not finitely generated, then which means that there exists a collection of infinitely many elements which forms a minimal generating set, and that gives me an infinite chain, which, see, if I have a, if this is alpha in I, let's just write n in n. Suppose this is a subcollection of generators, minimal generators, then I can always, and if I take Mn to be the module generated by x1 up to xn, then M1 is contained in M2, contained in M3, contained in M4, and that will be a strictly increasing chain and that never terminates, which means if your module is not finitely generated, it cannot be Noetherian. Okay. Now if a module is Noetherian, can we say that it has to be a finitely generated A module? How do you say so? Okay, so let us suppose M is M is Noetherian. That implies that M is finitely generated. That is what we showed just now. And if it is not finitely generated, then there exists a infinite chain. Now suppose we are trying to see if it is if and only if. Suppose M is a finitely generated A module. We are not saying, we have not said anything about A, okay. It is a finitely generated A module. Can we say that M is Noetherian? See, for example, in this case, suppose if this is my A and this is my M, then is M finitely generated A module? No, I am saying this ring is A, which is also equal to M. It is finitely generated because 1 is a generator, right? But is M Noetherian? No. Okay. So we want something more. If I take A is an arbitrary ring and M to be a finitely generated A module, that need not necessarily say that M is Noetherian. So, this is not enough. What we have is, suppose every submodule of M is finitely generated. Every submodule is finitely generated. Okay. Can we say that M is Noetherian? So, I want to say whether M satisfies ascending chain condition or not. So, let us start with a chain. Let M naught contained in M1 be a chain of submodules of M. Now, how do I say whether this is finitely generated or not, or I mean whether this terminates or not? See, from this chain I have to find a submodule. What should be? See, if I get a submodule, I can say that it is finitely generated. So, if I take N to be sum of Mi, I from 1 to infinity, 0 to infinity. What if I take union? It is a chain. This is same as union as well. Right. Then this is indeed a submodule of N. Take N to be this, then N is an A submodule of M. That implies N is finitely generated, and that implies, so N is finitely generated means it has a finite generating set. So, let x1 up to xm be a generating set for N. Now, what do I do? I look for the least k which contains all of them. They are finite, this set is finite, therefore, it has to be somewhere at some finite stage, this will be contained in all of them. That means N will be contained in that particular module, submodule. That means N will be equal to that, which means from there it terminates. Okay. So, let k be the minimum I such that x1 up to xm is contained in Mi. Therefore, xk will be mk will be equal to, if those elements are there in mk, that would imply that N is contained in mk, but by definition all mk's are contained in N, that implies N is equal to mk, and that would imply that N is equal to mk equal to mk plus 1 and so on. So, therefore, the chain terminates. That implies M is Noetherian. Okay. So, we are saying here that if every submodule of M is finitely generated, then M is Noetherian. Here we showed that M is Noetherian implies M is finitely generated. Can we modify this and say that every submodule of M is finitely generated? The proof just simply goes through, right? Instead of, suppose there exists a submodule which is not finitely generated, we still can generate the same, in the same way you can generate the ascending chain condition which never terminates. So, therefore, we can say that every submodule of M is finitely generated. So, what we proved now is that then M is Noetherian if and only if every submodule of M is finitely generated. Okay. I will leave it to you to write down this part of the proof. Okay? Complete it. Now, suppose I have a module M and a module N. Okay. If I have a strictly increasing chain which never terminates here, that will give me a strictly increasing chain which never terminates here. Okay. I have an on-to map, or in other words, if this is Noetherian, then this is Noetherian. Right? Similarly, if I have a descending chain which never terminates here, then I have a descending chain which never terminates here. Look at the pullback. See, if I have any submodule here, I can have a phi inverse Ni. If this is, if I have a chain like this here, that will give me a chain like that here, and this is never terminating will imply this is also never terminating, or in other words, if this is Artinian, this has to be Artinian. Okay. So, let M and N be A modules and phi from M to N be an onto A module homomorphism. Then if M is Noetherian, respectively Artinian, then so is n. That is, n is Noetherian and respectively Artinian. Follows directly from the surjectivity property. If this is Noetherian, then this is Noetherian, this is Artinian, this is Artinian. Now, what happens if I have a, suppose I have an exact sequence. Okay, by the way, this is the converse true? If this is Noetherian, for example, if n is Noetherian, can we say m is Noetherian?
We can take the sequence and suppose we map first sequence to some set and map all the sequence to the same set.
We need what we need is little more, but this is, see, if I have a surjective map, for example, I will tell you this k x1 x2 so on to k x x1, there is a surjective map, right, xi homomorphism which says put xi equal to 0 for all I bigger than equal to 2. That is a surjective homomorphism from here to here. This is Noetherian, but this is not. Okay. So, the converse of this is not true, that if n is Noetherian, then m is Noetherian, we cannot say. So, what more do we require? Let us look at consider the exact sequence. So, let me write, let 0 to m prime to m double prime to 0 be an exact sequence of A modules. Now, if m is Noetherian, this is Noetherian, right. Now, m is Noetherian, what can you say about m prime? How do you say that? We need to use the previous proposition. If m is Noetherian, every submodule of m is finitely generated. In particular, if I look at the collection of all submodules of m prime, that is a subset of the collection of all submodules of m, or in other words, every submodule of m prime is finitely generated, which means m prime is Noetherian by the previous proposition. So, if m is Noetherian, both of them are Noetherian. What about if m double prime is Noetherian? We have already seen the example that need not necessarily imply m is Noetherian. What if we impose both of them are Noetherian? Suppose we say that this and this are Noetherian. Can we say this is Noetherian? Suppose m double prime and m prime are Noetherian. Can we say that m is Noetherian? The idea is what you said. How do you prove that it is Noetherian? We can, one way is to use this, that every submodule is finitely generated. So, let us look at, let n be an a submodule of m. If I say that n is finitely generated, I am through, right. Now, how do I do this? I know that m prime and m double prime are Noetherian. Okay. Now, see, we do not know anything about n. How do we bring in these two, using n, how can we get some submodules of m prime and m double prime? Then n intersection m prime is a submodule of m prime. Right? But m prime is Noetherian, therefore this is finitely generated. Okay. Let n intersection m prime be generated by x1 up to some x r. Now, can you think of some other submodules of m double prime? What is m double prime? M double prime, you can think of it as isomorphic to m mod m prime, and consider the submodule of m mod m prime, n plus m prime mod m prime. This is a submodule of m mod m prime, which is isomorphic to m double prime, which is Noetherian. Therefore, this is n plus m prime mod m prime is finitely generated. Okay. So, let y1 bar up to ys bar, this, the A span of this be equal to n plus m prime mod m prime. This can also be seen as n mod n intersection m prime. So, therefore, what should I claim? N is generated by x1 up to xr, y1 up to ys. This is again like rank nullity theorem. The philosophy behind the proof is very similar to the proof of rank nullity theorem. So, I start with an element y in, so let us start with some element n in n. Look at its, if this is, if n belongs to n intersection m prime, then n is summation ai xi I from 1 to r. If x is not in, if n is not in n intersection m prime, then this is non-zero in n plus m prime mod m prime, which is isomorphic to n mod n intersection m prime. Therefore, I can write n bar equal to summation ai yi I from 1 to s. I will write this as b j y j, j from 1 to s. And that implies that n minus summation b j y j belongs to n intersection m prime. Therefore, this implies, but n intersection m prime is finitely generated and it is generated by x1 up to x r. Therefore, n minus summation b j y j, this is summation a I x I from 1 to r. So, what we have shown is that n is finite, I mean n is generated by these x1 up to x r and y1 to y s. So, I will simply write like this, n is equal to this. For some b j in A, for some a I b j in A. So, that implies n is finitely generated, that implies m prime is Noetherian, sorry, m is Noetherian. Okay. So, therefore, this is what we have shown is that then m is Noetherian if and only if m prime and m double prime are Noetherian. Okay. And this is precisely the proof. I will leave it to you to verify that the same is true for Artinian. Okay. So, this is Artinian if and only if this is Artinian. If I have an exact sequence, then one is Noetherian if and only if the other two are Noetherian. The middle module is Noetherian if and only if the other two modules are Noetherian, and similarly Artinian. Okay. So, in fact, this is, I will leave it as an exercise, that what we proved here is that suppose 0 to m prime to m double prime to 0 is an exact sequence of A modules. If m double prime and m prime are finitely generated A module, then so is m. We have just simply created a spanning set for m from the spanning set for m prime and m double prime. And if you look at the proof, it is very similar to the proof of if A is Noetherian and m is a finitely generated A module. This is I could have stated immediately after the first proposition. Noetherian, Artinian, then m is Noetherian. Yes. Yeah, so we need one more property, I guess. Before this, yeah, I need one more property. Let me. This is a corollary of the previous, the exact sequence result. If M1 up to Mn are Noetherian, respectively Artinian, then so is so if M1 and M2 are Noetherian, then you have this exact sequence M1 to M1 direct sum M2 to what is M1 direct sum M2 modulo M1? It's isomorphic to M2, right? This is an exact sequence. This is, if this is Noetherian and this is Noetherian, then this is Noetherian. Similarly, if this is Artinian, this is Artinian, then this is Artinian. Okay, so another corollary is if A is Noetherian and M is finitely generated, so here I will write Artinian A module, then M is Noetherian. Again it follows from how do you get this? How are finitely generated modules characterized? Quotient of some a power n, right? So, from on to homomorphism, right. So, if A is exact, sorry, A is Noetherian implies a power n is Noetherian. Direct sum of Noetherian modules is Noetherian. Therefore, A is Noetherian implies a power n is Noetherian, and you have a onto homomorphism, therefore M is Noetherian. Similarly, if A is Artinian, a power n is Artinian, therefore M is Artinian. If A, yeah, another corollary is if A is Noetherian, respectively Artinian, and I in A is an ideal, then A mod I is Noetherian. Again it follows from the exact sequence A to A mod I. So, we have already seen some examples of rings which are neither Noetherian nor Artinian and so on. So, here another one more important example, that if I look at this X be a compact Hausdorff space, and x1, x2, yeah. So, look at this Cx to be set of all continuous real valued functions. This is a ring under pointwise addition multiplication. We have looked at this for x equal to the closed interval a b, but one can do this for any compact Hausdorff space. And I look at this, suppose x1 contained in x2 be a chain of closed subsets of x. Okay. I write I to be set of all f in Cx such that f of a is 0 for all a in xi, vanishes on every points of xi. Then this is an ideal in, one can check exercise that I is an ideal in Cx and I1 is contained in I2 contained in so on. So, if this is a strictly decreasing chain, then this is a strictly increasing chain, and that would imply that Cx is not Noetherian. Okay. So, is Cx Artinian? Think about this.